So imagine rolling a dice over and over again every time you get a number between 1 and 6. If you took those numbers that you rolled and then averaged them, what would that average be? If you stood there and did it all day long, what would that average be? Well, we're going to try to simulate that with a spreadsheet assignment here and the use of a confidence interval. So in column A, I've already rolled the dice 100 times using the ran between formula we used in spreadsheet assignment 7. What I want to do now is copy this. So I'm going to copy it, go to column B, and what I'm doing here is in column A I have a formula and I want to freeze these numbers so they don't keep changing on me. So I'm selecting column B, right-clicking or command-click on a Mac, paste special, and paste the values only. So notice these changed there. These are actual numbers. These are formulas that will continue to change. So I'm going to use the numbers here in column B. And if I get my sample mean, you probably should check to make sure that you do have 100 there. And I don't have any headers, so I do want to go to row 100. That's correct. I need to get an average. So make sure that you take column B here instead of column A, because again, these values will continue to change. Then the population standard deviation I'm giving to you, put it in as a formula. Put it in as the formula square root SQRT of 35 divided by 12. And how we get this, if you're interested, feel free to email me. It's a little bit beyond the scope of this course, but we're using that as the known population standard deviation of rolling a dice. And then we need to get the standard deviation of sample means. This is the weird one. This is the one that if you can really understand this, you'll be fine the rest of the course. What it is, if I did this experiment with 100 rolls and each one of you did this experiment, let's say each student at EMU did this experiment with 100 dice rolls, and then we took the standard deviation of all of our sample means. So my sample mean here is 3.42. Maybe yours is 3.25. Maybe someone else's is 4.02. Everybody has a sample mean. If we just put those in as rows of our spreadsheet and took the standard deviation of all those, that would be the standard deviation of sample means. And that's a very key value that we'll be working with here. To get it in this case, using the central limit theorem, we take the standard deviation divided by the square root of our sample size. So the sample size here would be, it's represented by the lowercase n, and it's the number of times that we've rolled the dice. So in this case, we have 100. So notice that this standard deviation is much less than this standard deviation. In fact, it's 1/10 of this one because we're using a sample of size 100, and the square root of 100 is 10. The next thing we have to do is actually estimate, use our values that we've gotten so far to estimate our margin of error. In other words, this 3.42 that we got right at the very beginning by averaging our sample is really our best guess at what the entire population mean is. And by population mean, I mean if you sit there and rolled for the rest of eternity, roll this dice and take the average of them, what that average would be. That's called the population mean in this case. And 3.42 is our best guess based on this sample. But we need more than a best guess. We want some kind of range to see how close this estimate actually is. So that's what we're doing here with this margin of error. We want to see 3.42 plus or minus how many is what we're fairly confident in. To get that, we take the standard deviation of sample means times, and here's where it depends on how confident we want to be. If we're creating a 95% confidence interval, we want to multiply that by 1.96. We want 1.96 of these standard deviations. That way we create a range that captures 95% of the population mean 95% of the time. and that would give us 0.33. So this number that we have is probably within, give or take, 0.33. And to write that out formally, we'll just take this estimate, subtract the margin of error, and then take this same estimate and add the margin of error. So a couple quick things to point out there. When you're calculating this margin of error, a lot of times people will round to 2 for convenience, or maybe they forget this exact number. Maybe it makes the calculations easier. That would be fine if you want to do that. Also, this is an actual range. So this is the lower bound of the range. This is the upper bound of the range. What we're saying is the population mean should be 95% sure that the population mean is actually between these two numbers. Your two numbers will be different because they'll be based on your 100 rolls, and you may not actually catch the true mean. In this case, I did catch it. The true mean is 3.5, so my confidence interval caught it. Your correctness of this process has no connection with whether or not you actually catch the mean. By randomness alone, 5% of the times you won't catch the mean, and that's important to realize, that the 95% confidence interval doesn't always get the population mean, but in this particular case it did.